So I'm going to pick up where I left off in the last video, since it's a really important point. This R is always going to be from the center of a planet. If we're dealing with planets. Say you're dealing with two large balls. It's always going to be from, so say you have a problem that's like this. You have two balls that looks like this. You're given maybe this distance here, and then this distance here. It's always going to be from the center of your objects, not from the surface. So for this problem that we were given, you don't want to, I'm going to draw it here. This is Mars. Here's the satellite. You don't want to take this distance, let's call it D, as your R radius in your gravitational equation. So you don't want to substitute D in here. So this would be incorrect with it being D squared. This would be incorrect. And it's a common mistake just to take the distance from the surface of an object to the other one. You need to take it from the center of the object. Take R from the center. So that's key. Moving on to question 4, you stand on the floor of an elevator at each instant shown. Is the normal force on you less than your weight, equal to your weight, or greater than your weight? So we did some examples like these. I mean, this is a little different. It's just worded a little differently, but we dealt with elevator problems within our note packet. The elevator, so let's draw our forces. The elevator is at rest. Well, if it's not moving, what do we know about the sum of the forces? The acceleration is 0, so the sum of the forces must be 0. So we have a weight force downwards. We have a normal force that's upwards that is equal and opposite to the weight. So we know that the normal force, which is what we're reading off our scale. So I'll take a step back and talk about it. So, you know, say a bathroom scale that you have. When you go to measure your weight, what the scale is actually measuring is the force that it's applying upwards on you to balance the weight. Since you're not moving when you're in the bathroom, you know, measuring your weight, the acceleration is 0. So that normal force upwards is an accurate representation of your weight. It equals your weight. So what it's reading out is the force that it's pushing up on you, not what your actual weight is. So if you jump up and down, or, you know, if you redistribute your weight, so you're like pressing on your toes, you're going to change the reading on the scale. Go try it out. And that's because you're having an acceleration at some point. You know, if you're pushing up on your toes, you're accelerating. So that's going to change the reading on the scale. And it's going to differ from your true weight, which is when you're at rest. And that reading is opposing your true weight. So the weight is always the same. You know, that's determined directly from your mass. As long as you're near the surface of Earth, your weight does not change. What can change is the normal force, because that is going to match whatever your acceleration is. So if you don't have any acceleration, then the normal force is going to oppose your weight force equally. But if there is a net acceleration, then the normal force is going to change. We have experience with this. You know, driving on top of a hill or reaching below a hill or going down a hill at the bottom, what we feel is different. We feel differently. We feel heavier or we feel lighter. And that is the change in the normal force. Our weight's not changing. We're not losing mass or gaining mass. It is that normal force is what we feel. That's the sensation of the weight. So taking a look at 2 now, the elevator is going up and speeding up. So going up is a positive direction. Speeding up tells us A and V must be in same direction. This is a recall of modules 2 and 3. So when we talked about how physics builds on itself, this is what we're talking about. These are concepts that we dealt with in previous modules, but they're coming up again because they are all interconnected. Physics describes the world around us. Everything's interconnected. Nothing's kind of sliced together and operating in a bubble. All of these concepts build together to explain what's happening around us. So A and V are in the same direction, so we're speeding up. So the acceleration is up. That's the key. This is what we were after. It's determining what is the acceleration. Why? Because that tells us what the direction of the net force needs to be. Because remember, sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. So, whatever the acceleration direction is, the net force better be in that direction. So the acceleration is up, so the net force needs to be up. So what should we draw the normal force? Should the normal force be greater than, less than, or equal to the weight? Well, the weight doesn't change. That's the same as over here, which I should be more explicit with. Well, to get a net force upwards, it better be longer or have a greater force than the weight so that there is a net force upwards. So, for this one, this was A. Is it greater than, less than, or equal to? Well, the normal force or the reading from the scale is going to be greater than because that force is greater than the weight. So that's C. Drawing the weight so that it's the same as the other ones, here and here. The elevator is going up at a constant speed. So what does constant speed mean? That should be flashing in your head as no acceleration. Constant speed means velocity is not changing, which means acceleration is 0. Acceleration is, again, the change in velocity. No change in velocity, no acceleration. So if acceleration is 0, what do we know about the sum of the forces? Well, it's going to be no different than the elevator being at rest. The normal force is going to be equal to our weight force. And so what is that? That is... Oh, I made a mistake back here. Sorry about that. That's B, equal to your weight. And again, here, B is equal to your weight. Because there's 0 acceleration, the forces must cancel, so the normal force must be equal and opposite to your weight force. And then 4, the final, the elevator is going up and slowing down. The velocity must be in the direction of motion, which is up. So velocity is positive or up. We're slowing down. Slowing down is code for V and A, velocity and acceleration being in opposite directions. Again, this is from the previous modules. So, if we have acceleration downwards, what must the net force be if our acceleration is pointing downwards? Well, the net force must be pointing downwards. So, for that to happen, we know that the normal force must be less than the weight force. Let's make that explicit. There we go. So what would the reading on the scale be? Remember, the reading on the scale is what the normal force is. That reading should be less than your weight force, so A. So for question 5, we've got a problem that is very similar to the ones we dealt with in the note packet. We have this mass on an incline that's being pulled upwards. So this is a rough surface. This is going to involve friction. And we have motion on an incline. So what does that tell you automatically? So as soon as you see this problem, what should be flashing in your head is that I need to choose a tilted coordinate system. Because we have motion that is happening at an angle. So we need to choose a coordinate system that matches the incline. And the reason why that is, again, is so that your acceleration is going to be in a single direction. So in this case, the x direction or the positive x direction. And so the process for this problem follows exactly what we've done in the note packet. We have 4 forces. We start by drawing our weight force downwards. We have friction opposing our motion. We're going up the incline, so the force of, what kind of friction do we have? Kinetic or static? So we have a block that's sliding along an incline. So sliding is a key word for kinetic, because when you slide, your object is moving relative to the surface, and that is kinetic friction and not static. We have a normal force that is perpendicular to the surface, and that is from the incline acting on the block. That normal force should be drawn shorter than your overall weight vector, because what is that opposing? We have no acceleration in the y direction. AY is equal to 0. So it must be opposing the y component of weight, Wy, which is always going to be less than the total weight vector. Your component is always going to be smaller than the actual vector. It's by definition. And then our final force, that is what's pulling the block upwards. That's going to be a tension force, T. Should that be greater than or less than the frictional force and the x component of weight? Well, if the block is accelerating up the incline, then we know that the tension must be greater than the weight force in the x direction and the frictional force combined, because the net force must point in the direction of acceleration. So you draw out your free body diagram, you put it in your table, and again, you sum the forces in the y direction here, you take it straight from this table right here, and you substitute it directly into that equation. That is where your forces come from. It comes straight from your table, which comes straight from your free body diagram. Again, you do the same thing in the x direction down here. Here we have 3 components in the x direction. So you sum those forces and you're able to solve for the acceleration.